Hi, welcome to this third video in the lecture series Based on Statistics, or actually machine learning. And today we are going to look at three topics which are quite related to each other. That is kernel series and local linear regression. You could say that they're all related to each other because of the fact that they're all related to the topic of non-parametric regression analysis. So in order to start this topic, I would like to start with something that, well, I guess you already have seen before. However, this is going to be more like an introduction to the things that I'm going to discuss later on, and that is kernel density estimation. In order to introduce kernel density estimation, I would like to say that sometimes we would like to estimate the density of the data distribution. This is a topic that I already talked about a couple of times before, because of the fact that I already said a couple of times before that, well, statisticians generally assume that the data come to us in a random way. And that means, of course, that the data as represented by a factor of those things that we do observe, well, that data has by itself a distribution. And more in particular at the moment that our data is going to be continuously distributed, then it also does have a density. So therefore the question arises, how can we estimate that particular density? By the way, take into account that this is a topic which is not related to supervised machine learning, but this is actually related to unsupervised machine learning. Unsupervised machine learning is about, well, how to get information of the data distribution, and that is what this and the next couple of slides is about. So these slides are actually more related to unsupervised machine learning rather than supervised machine learning. Well, to come back to the question how we're going to be able to estimate the density of the data distribution, one thing that we can say that if we know, or at least at the moment that we're going to assume the parametric form of the data distribution, then we can simply estimate the parameters with maximum likelihood. We can say even more than that because of the fact that maximum likelihood is, in this case, by far the best method that we can ever use. And the reason behind that is because of the fact that maximum likelihood is consistent. It is also asymptotically efficient. Well, of course, there are some bad things to say about maximum likelihood, such as that it could be biased, but we should realize that it's at the moment that it's going to be biased, then generally every other alternative is going to be biased as well. And that makes the maximum likelihood procedure unanimously the best method to use in this particular case. So in that sense, there's not so many bad things to say about maximum likelihood. But you should realize that in many situations, the parametric form may not be known. And it may even be the case that we do not want to make any assumptions with respect to the parametric form. Well, if we're in that situation, then we are in the world of non-parametrics. And in this case, we would like to estimate the density. And the most used density estimator in non-parametrics is a so-called kernel density estimator. How does that look like? Well, first a little bit of notation. Here, because of the fact that we're going to look at the density, we are going to have this small f that we have over here for the density function. In this case, we have in the subscript y in order to indicate that we're going to look at the density of our random variable y, and we're going to evaluate it in this small y that we have over here. So in general, density function looks like this. And what we want to do is that we just want to estimate it in a particular point. Well, because of the fact that this is going to be an estimator, we're going to place a hat above it. And then what is our estimator? Well, it is generally a sum of what we could say a kernel function evaluated in yi minus y over h. And then we multiply this by, well, 1 over the number of observations, but we also divide this by this h that we have over here. But there are a lot of things to say about this kernel density estimator, not in the least because of the fact that there are a couple of things that I have now introduced. I have introduced this kernel function that we've over here, and I also have introduced this, say, h that we have over here, which is generally called the bandwidth. Well, I'm going to say much more about the kernel function at the next slide, but let's first of all, it might be nice to get a little bit of an idea what this kernel density estimator does. Well, the kernel density estimator is based on the idea that at the moment that we're going to have relatively many observations very close to the point in which we would like to estimate our density, this point y that we've over here, well, then in general, we expect the density itself to be high. That makes sense, of course. The moment that yi, or this y that we have over here, would have been discrete, that's not the case here because of the fact that otherwise it doesn't make any sense to try to estimate the density function. But in the case it would have been discrete, then in order to estimate the probabilities in that particular case, well, what could we have done? Then we could have just counted up the number of observations yi that would have been exactly equal to this y that we have over here. But that we cannot do in the case that we are going to look at a continuously distributed random variable, because of the fact that we do know that no yi will ever be exactly equal to this y that we have over here. But still, we can expect that at the moment that we are going to have a lot of observations, which are going to be very close to our y, then at least at the moment that this density function that we have over here is going to be continuous, then we can expect that the density function is also going to be high in those, say, places and those y's for which there are a lot of observations very close to that particular y that we have over here. And that's exactly what this estimator does. It counts the number of observations that are very close by this kernel function. And more in particular, this kernel function is going to weight these particular observations. At the moment that an observation is going to be very, very close, then of course the difference between yi and y is going to be small. Then this kernel function is also going to be large. Kernel functions in general are going to give you large outcomes at the moment that we are going to be very close to zero. And of course, that is going to be the case if yi minus y is going to be small, if the difference between yi minus y is going to be small. So therefore, at the moment that you have many, many observations, for which the difference between yi minus y is going to be small, then there are also many, say, observations for which this k function, this kernel function, is going to be high. And then in that particular situation, also our estimator is going to be high, our estimator of our density function. On the other hand, if we have many, or at the moment that we have very few observations for which the yi's are going to be close to this y that we have over here, well then this thing that we have over here is almost everywhere equal to zero. And therefore we should realize that then also the density estimator is going to be low, but also that makes sense is if there are very few observations very close by our y that we have over here, well then we do expect that there is not that much, say, mass over there, probability mass over there, and therefore we also expect that the density function is going to be small over there. But realize that this also is related, how close you are with respect to this y that we have over here is of course also related to this h that we have over there. If h, the bandwidth, is going to be relatively large, well then it is still allowed to be somewhat different from y at the moment that we're going to look at an observation yi that we have over here, because of the fact that then we are going to divide by a relatively large number, and that implies that we still are going to have a small number over here, and therefore the kernel function is going to be high. However, if h, the bandwidth, is going to be really, really small, then even a small difference between yi and y will give us a large value over here, and therefore a small kernel function that we have over there. Well, there's much more to say about the bandwidth, but that I'm not going to do over here. Let me concentrate now on the kernel function. as already said, a kernel function is, you could say, just a mathematical function with the specific characteristic that it is high around 0. More in particular, we're going to assume that kz is going to be symmetric around 0, and it's going to be continuous. In addition to that, we're also going to make a couple of assumptions with respect to the integral. First of all, the integral must be equal to 1. And if we multiply the function kz by z, then the integral should be equal to 0. And we're also going to make this assumption that we're over here. But in fact, the last assumption is the most important assumption. And that is related to what I already said before, that at the moment that we are going to be very close to, say, 0, then the kernel function should be relatively high. But it should also be the case that at the moment that we are too far away, then the kernel function should be really, really small and ultimately equal to 0. Because if we have an observation in which the difference between yi minus y is large, well, then we don't want to take that into account, of course, in our kernel density estimator. And that's exactly what we have over here. We could have one of two different assumptions. First of all, we could have that kz is simply equal to z, 0. At the moment that z in absolute values is larger than some threshold value x, well, that is exactly what we have said before. At the moment that, well, the difference between yi minus y is going to be too large, then simply this kernel function is going to be equal to 0. We could also have another situation in which z multiplied by kz, z in absolute values here, is going to converge to 0 if z goes to infinity. Well, that means that this kz is allowed to be positive, say for any value, but we should realize that it should converge to 0 very quickly. Now the question, of course, arises, what kind of kernel functions could we use in this case? What kind of kernel functions are there used in non-parametric statistics? Well, a very famous kernel function is this kernel function that we have over here. It's equal to an indicator function that indicates that z in absolute values must be smaller than half. How does that look like? Well, it is possible to then look at this figure that we have over here. Here we have on the x-axis, we have the different values of u. And on the y-axis, we have the ku, the kernel function evaluated in these values that we have over here. And then we see that this uniform kernel is actually almost everywhere equal to 0. However, in between minus a half and a half, it is exactly equal to 1. Well, the reason why this is called a uniform kernel is, by the way, because of the fact that this is exactly the uniform or the density of a uniformly distributed random variable. Actually, in between minus a half and a half. So that is the reason why this is called a uniform kernel. There's a little bit more to say about this uniform kernel because of the fact that at the moment that we're going to use a kernel density estimator, and we are going to use this kernel function that we have over here, well, then what we are going to get as an estimator is a so-called histogram. I think that a lot of people have heard about histograms before. A histogram is nothing else than that we are going to, well, divide our data into different bins, and then we're going to count the number of observations that we have in a particular bin. We're going to make a nice picture with respect to that. Well, you should realize that that's actually nothing else as using or estimating a kernel density estimator and then using this uniform kernel that we have over here. So therefore we can say that a histogram is actually a kernel density estimator, but of course it's not the other way around. Well, apart from the uniform kernel, we can also use other kernel functions. One very famous function that is used is a so-called normal kernel function. The reason why this is called a normal kernel function is because of the fact that it's exactly the density function of a standard normally distributed random variable. It looks like this bell-shaped function that you already know of from a long time ago. That is this, say, kernel function that we have over here, the normal kernel function that we have over here. Well, what is good about this kernel function that we have over here is that it tries to take into account a couple of drawbacks with respect to the uniform kernel that we had over there. You should realize that uniform kernel has a couple of things which are not so nice. First of all, you should realize that at the moment that we're going to look at this uniform kernel, then we see that it can only take two different values. It's either equal to 0 or it's equal to 1. In terms of the weights with respect to the kernel density estimator that we have seen before, that means that every value can only have two different weights. This thing that we have over here is either equal to 0 or 1. That means that any observation that we have over here either gets a weight equal to 0, in which case it's not going to be taken into account for the final estimator that we have over there, or it's equal to 1, and then it's going to be taken into account by the maximum. And you should realize that that doesn't matter whether we're here at 0. 0 means in general, of course, that the observation that we have at hand is exactly equal to the point where we would like to estimate our density function, or whether it's here at the border. But you should take into account that the difference is quite large, of course. Here we have an observation which is exactly equal, and here we have an observation that can be quite different. So therefore, we should realize that these things are going to have exactly the same weight, but they are actually quite different from each other. Well, a more difficult problem even arises at the moment that we're going to look at this drop over here and that drop that we have over there. For example, if we're going to look here at the observations that we have over here, if we compare an observation that is just below this 1/2 with an observation that is just above 1/2, take into account that that means, of course, that the difference between y and yi, the observation that we're going to look at, is either a little bit below 1/2 times the bandwidth or a little bit above 1/2 times the bandwidth. Well, these observations are going to be taken completely differently according to our density estimator. The first observation is going to get the full weight, even though it might be quite different from 0, whereas the second observation is going to be having no weight at all. It's always equal to 0. And that is not so nice. And the reason why that is not so nice is because of the fact that if we would have changed the bandwidth only a little bit, that could actually have changed our kernel density estimator completely. And that is the reason why we typically like to look at other kernel functions, such as this normal kernel function that we have over here. The nice thing with respect to the normal kernel function is that it's immediately clear that at the moment that you have an observation exactly here at 0, that always gets the highest weight. And any other observation is going to get lower weights, depending on how far they are from, say, the observation y that we have over here. So the further you are away with respect to the observation from the point where you would like to estimate your kernel density estimator, well, the lower is going to be the weight. That was, of course, also true over here, but it's not going to drop as ad hocly as we had before with respect to this value of 1/2 that we have seen before with respect to the uniform kernel. So that's actually great, and that is a reason why it might be a good thing to use the normal kernel function instead of the uniform kernel that we have been using over here. We are going to see that weights actually depend always on the distance between, say, where you would like to evaluate your density function and the observation that we have. However, you should realize that there are still a couple of things which are not so nice with respect to this normal kernel function. And that's especially related to the fact that even though, say, weights exactly at 0 are the highest, well, they are not that different, for example, in the case that we are here at a distance 1/2 from, say, the observation in terms of the bandwidth. And we even see that at the moment you're 2 times the bandwidth from the observation, then still you get some weight over here. That's probably not that nice. And therefore, typically what we're going to do is that we're neither going to look at the uniform kernel or the normal kernel. What we usually use is this Abednikov kernel that we have over here. It's immediately clear that this Abednikov kernel combines the nice characteristics of the 2 kernel functions that we have looked at before. First of all, we see that we are going to have the highest weight at 0, and we immediately see that actually the weights go down quite quickly at the moment that we are a little bit off from, say, the observation that in which we would like to, or the value at which we like to estimate our density function. And we do see that it actually goes down here to 0 at the moment that we are 1 bandwidth from, say, the point in which we would like to estimate our density function. Here, and there we have exactly the same. Now you might of course say like, well, but this looks a lot like what we had with respect to the uniform kernel. Here we also see that the weights at a particular moment in time, they are going to drop down to 0. But you should realize that that doesn't, it's not really a drop, a non-continuous drop as what we had over here. In this case, it's still continuous, though not differentiable, of course, but it's still continuous. And that means that observations that are just a little bit above 1, and you're going to compare them with observations that are just a little bit below 1, well, they are different, of course, because of the fact that the ones just above 1 have no weight, whereas these ones have a little bit of weight, the ones just below 1. But you should realize that the difference is not that large because of the fact that still these observations just a little bit below 1, they have a weight, a positive weight, but the weight by itself is not that large. Okay, I would like to go on, and I would like to go on with the next topic, which is the kernel regression or the Nadaraya-Watson estimator. Like what we have done with respect to non-parametric density estimation, we can also look at the non-parametric regression estimation. That's exactly what I'm going to do right now. Suppose that we have the following model. We have yi at the left-hand side, and the right-hand side we have gxi plus u1, where xi is going to be observed, and we're going to assume it to be continuously distributed. And in addition to that, a main assumption that I'm going to make is that u and x, they're going to be uncorrelated with each other. Another, but that is only notation, assumption that I'm going to make over here is that the mean of ui squared is going to be denoted by this sigma squared u conditional net. So I'm going to allow for heteroscedasticity, and of course, because of the fact that this is the second moment, but the first moment is equal to 0, this also is the variance. Well, the most important thing with respect to this model is that I'm not going to make any parametric assumptions with respect to the function g that we have over here. So unlike at the moment that we're going to look at ordinary squares, or more in particular at the moment that we're going to look at the linear regression model, I'm not going to assume here that the function g that we have over here is a linear function. Well, it is even the case that unlike what we typically do in the non-linear regression model, that we are going to have here not a linear, but a non-linear function that we have over here, I'm not going to make any parametric assumption. So in a standard non-linear regression model, we are going to assume that this thing that we have over here, even though non-linear, it is known to us. We do know what a parametric form is. And therefore, the only thing that we need to do is to estimate the parameters. That's not what I'm going to do over here. Essentially, I'm going to make no assumptions, or at least no parametric assumptions with respect to this function g that we have over here. Of course, we have to make some assumptions, some regularity assumptions with respect to this g that we have over here, but I'm not going to go into details over here. Still, what we would like to do, even though we don't want to make any assumptions, we would like to estimate this function g that we have over here. How can we do that? Well, the first thing we can do is that we can rewrite this thing a little bit. The first thing we can do is that we can look at the mean of y conditional x equal to x. What is that? Well, that's not too difficult. What we first can do is to substitute in here the model in there. And then we get at the right hand side the mean of gx plus u conditional x equal to x. But then what we can do is that we can realize that the mean of a sum is sum of means. So therefore we get these two means that we have over here. And then we can realize that this x, this large x, is equal to that x that we have over there. That one is equal to little x. So also this thing is equal to little x. And then I can realize that this, even though we take a mean over here, is of course nothing else as gx itself. So therefore we can simply write it like that. And then I can realize finally that this mean that we have over here is by assumption equal to 0. So therefore we can simply write the mean of y, condition x equal to x, equal to gx. This is actually a thing that we have already seen before in a more general context, but now we have proven it again. And well, what we can do is that we can write it like this, but of course we can also write it the other way around. We can also say that our function gx that we're looking for is simply equal to the mean of y conditional x equal to x, which what we use is the question how we're going to estimate this g function by looking at this mean that we have over here. Well, and then the next thing that we can do is that we can rewrite this a bit. The first thing that I'm going to do is that I'm going to realize that the mean is of course nothing else as an integral, so that we're going to write it as an integral. This integral that we have over here, where now yx is going to be the support of y conditional x equal to x, and we're going to of course integrate with respect to y, and we're going to, well, now multiply this by the density, the conditional density y conditional x. I'm going to assume that this y is going to be a continuously distributed outcome variable, and that makes sense because in the fact that x is already continuously distributed. So therefore we're going to write the density over here, and we multiply it by dy. Now the next thing we can do is that we can look at Bayes' rule. I know that this lecture series is called Bayesian statistics. As you may already know, I'm not going to say too much about Bayesian statistics, but I'm going to have Bayes' rule here. Bayes' rule, I'm pretty sure that you have heard about that before, but Bayes' rule is actually nothing else as a rule that says that if we have the probability y conditional on x, then we can also write that as the probability of y condition on, the probability of x conditional on y multiplied by the probability of y divided by the probability of x. Well, this Bayes' rule actually directly follows from the definition of conditional probability. In addition to that, what I can say actually about Bayes' rule is that Bayes' rule has been for a long time, well, the central topic in artificial intelligence. Machine learning is related to artificial intelligence. And you should realize that for a long time, we have been using Bayes' rule for artificial intelligence. Now these days, it's not that important anymore, but still you should realize that this was for a long time the central rule that was used in artificial intelligence. Well, what we could say is that this Bayes' rule holds for probabilities, but it actually also holds for densities. So therefore we can even say that the density of y conditional on x is equal to the density of x conditional on y multiplied by the density of y divided by the density of x. Well, that's very useful in this case because of the fact that, remember from the previous slide, that we have had this relationship that we have over here. And now what I can do is that I can simply substitute in this thing that we have over here in there, because of the fact that this f that we have over here is exactly equal to the left hand side that we have over there. If I do that, then I get almost the thing that I want to have, but I would like to still rewrite this a little bit. Well, this is a trivial rewritings because of the fact that what I'm going to do is that I'm going to put this outside of the numerator, and this one I'm going to get inside of the numerator. Then I get this relationship that we've over here. Well, this is actually quite a nice relationship because of the fact that you realize that apart from this conditional support that we have over here, this now is actually another time a mean. It's a mean of y because of the fact that we have here this density of y. So integrate over the support of y, and we have here the density of y, and that means of course that it's going to be the mean of y with respect to this function that we have over here. So therefore we can simply write it the way I've written it over here. Why did I do that? Well, the reason is analogy principle. We should realize that what we have over here at the right hand side is actually nothing else, according to the analogy principle, a population mean. It's a mean over the data, and therefore it is called a population mean. And we do know from the analogy principle that at the moment that we would like to estimate a population mean, we can always estimate that consistently by its corresponding sample mean. And that's also what I'm going to do over here. That means in general, no expectation, but we're going to get summation. We're going to sum over all the observations that we have with respect to this function that we have over here, and we divide by n, and we get this thing that we've here at the right hand side. This now is the corresponding sample mean of that population mean that we have over there. So therefore, if we're going to define that as g hat x, then we should realize that this g hat x is going to be a consistent estimator of that gx that we've over there, because of the fact that that's what the analogy principle says. The sample mean is always going to be a consistent estimator of its corresponding population mean. And because of the fact we have now shown that this population mean is exactly equal to the thing that we wanted to estimate, g at x is going to be a consistent estimator of gx over here. So that's very nice. However, you should realize that in this particular case, we cannot really calculate this thing yet. And the reason behind that is because of the fact that we still have these density functions that we have over here. And these again are density functions of the data. So they're related to the data distribution. So in general, we do not know that. So the question arises, how can we estimate these things? Because if we cannot calculate them, we will try to estimate them. So what I'm going to do first is that I'm simply going to put here hats above these densities that we have over here. But now, of course, the question arises, if we replace them by estimators, how does these estimators look like? Well, one thing that we could do is that we could make parametric assumptions with respect to these densities that we have over here. It's the density of x1 and the density of x1 conditional on y1. But that would be a little bit strange, because remember that what we would like to do is that we would like to non-parametrically estimate, and therefore it would be a little bit strange if we are now going to make a parametric assumption over here. So therefore we would like to estimate all these functions over here as well, non-parametrically. With respect to the denominator, it's going to be very simple. What is this? This is nothing else than a density function. We do already know how to non-parametrically estimate density functions. That can be done by a kernel density estimator. But what about this thing that we've over here? Well, this thing is a little bit more difficult because of the fact that it's not the density of x1, but it's the density of x1 conditional on y1, actually evaluated in this yi that we've over here. Well, you should realize that the idea is exactly the same. What we could do, we could try to estimate this thing with respect to a kernel density estimate. How are we going to do that? Well, suppose for the moment, even though we don't know that that's actually not true, but suppose for the moment that this thing that we have over here is in fact the yi that we have over there is discretely distributed. Well, then in that particular situation, we do of course know that, well, what we could do then is exactly the same thing as what we did before with respect to looking at the mean of y conditional on x. At the moment that x was discretely distributed, remember that then I said that we could just use the average over the, say, x's that are equal to a particular level of x. But then we can do here as well. What we could do is, given the fact that the kernel density estimator is nothing else as something like a weighted mean over, say, the observations of the x's, what we can do in this case is simply, given the fact that we would like to condition here on the y's, we can only look at those observations for which yj is exactly equal to the thing that we condition upon, and that is in this case yi. Take into account that the notation here is a little bit difficult because of the fact that we're going to see that here in this case, I'm going to add over here the j's, And the reason behind that is because of the fact that I conditioned already on the value of yi. But apart from that, it's going to be exactly the same as usual. So this is just a kernel density estimator, but take into account, we still have to do one additional thing. And that is that we now have to divide by the number of observations for which yj is exactly equal to yi. This would work very well in the case that the y's would have been, in this case, discretely distributed. Then we could have done this thing over here. For example, if y could only take two different values, 0, 1, then in order to get the density of, say, x conditional on y equal to 0, we just do the kernel density over those observations for which yi is equal to 0 in our sample. We could do exactly the same for the case that yi is equal to 1. However, we do know that the y's are actually continuously distributed. That makes it a little bit different. The question then, of course, arises, how many observations do we have in general for which yj is exactly equal to yi? So how many observations do we have in our data set that are exactly equal to yi in the case that the y's are continuously distributed? Well, the answer to that is, of course, only one. And that is, of course, the ith observation itself. The moment that we are going to have that j and I are exactly equal to each other, well, then, of course, we have here simply yi is equal to yi. These must be equal to each other, of course. But there will be no additional observation that will have exactly the same value of yi, because of the fact that that's the definition of a continuously distributed random variable. You cannot get a particular outcome exactly. So therefore, we can rewrite this a bit in our case. First of all, we know that this number of observations which yj are exactly equal to yi must be by definition equal to 1. So this thing is equal to 1. And in addition to that, we know that this indicator function is only equal to 1 in the case that this j that we have over here is exactly equal to I. So that means, of course, that we can rewrite the density function that we had in the previous slide by this thing that we have over here. Then if we are going to substitute everything into the equation that we had before, so remember this equation that we have over here, then we get this estimator that we have over here. G hat x is equal to this thing that we have here now at the right hand side. And you should realize that this is actually the famous kernel regression or Nadir-Watson estimate. Again, we have here kernel functions. Here we, of course, have a kernel function, but also in that one that we have over there, we can use the same kind of kernel functions that we have used before. For example, we could here use the very much preferable Epanechnikov kernel function. Note, by the way, that at the moment that you're now going to use a uniform kernel, remember that the moment that you use a uniform kernel in the density estimator, then you get a histogram. At the moment that you're going to use a uniform kernel, in the case that we are going to have kernel regression, then you also get a very famous estimator because of the fact that then you get the k nearest neighbor estimator. Okay, I would like to go on with the next topic, and that's the topic of series estimation. What we have done so far is that we have looked at a non-parametric estimation method for regression. You should realize that it's not the only estimation method that we can use at the moment that we would like to estimate a regression model non-parametrically. There are many others of them, and one very serious one is so-called series estimation. In that sense, it's good to recap that what we had so far. We had the following model. We had yi at the left-hand side, and we have gxi plus ui at the right-hand side. And the main assumption that we have been making is that u and x, they are going to be uncorrelated with each other. And what we would like to do is that we would like to estimate this g function that we have over here, even though we're not going to make any parametric assumptions with respect to that particular function. Well, that's of course a very hard, say, task. You should realize that it's going to be very, very difficult to estimate a function for which you're not going to make any assumptions. However, there is a very nice approximation theorem, and that is Weierstrass approximation theorem. Probably you remember it from calculus classes. What Weierstrass approximation theorem says is that for every epsilon larger than 0, there exists a corresponding polynomial, pkx, which is actually nothing else as a polynomial of the order k of this psi x function that we have over here. It's equal to, well, pkx. At the moment we're going to have here j equal to 0, then we simply have a 0 over here, because then we get psi x to the power 0, but that's equal to 1, plus, and then we get here for the second term, well, there's j is equal to 1, then we get aj psi x, plus of course a, well, 2 times psi x squared, a 3 times psi x to the power 3, etc. And what is Weierstrass approximation theorem says is that if you're going to use this polynomial that we have over here, that there exists always a polynomial for which the difference between gx minus pkx is smaller than this arbitrarily chosen epsilon that we have over there. Realize that this thing that we have over here is a so-called norm. It's a norm, and it's usually called the infinity norm. Realize that this norm that we have over here means that, well, even the maximum of this difference that we have over here should be smaller than epsilon, because we should realize that this is actually true for any particular value of x. So it should not be only true for one particular value of x, but this should be true for any x that we can actually think about, which means, of course, that even the maximum difference that we have over here should be smaller than epsilon for a particular choice of this polynomial that we have over here. That means that it is also always possible to choose a k for this epsilon that we have over here in such a way that the combinations of the aj's and the psi xj's that we have over there is going to give this, well, distance, this maximum distance that we have over here. That is Weierstrass approximation theorem. In words, it means actually nothing else is that we can always make the polynomial arbitrarily close to the function gx whenever we use enough terms k in the polynomial. So what it means is that it's always possible to get arbitrarily close to this function gx that we have over here, and take into account that this is actually true for any kind of function. Well, I'm not sure what exactly the, say, conditions of this Weierstrass approximation theorem is, but we should realize that we don't have to make an assumption that this, well, function that we have over here looks like a particularly parametric form. It doesn't have to be a polynomial itself. It could be completely different. And that means, of course, that we could actually use it for us. We can use it for our model because of the fact that that's exactly what we have over here. We have an undefined function g, and we now know that we can replace it actually by this function pkx that we have over there. So that's the whole idea behind series estimation. We simply replace our function g by this polynomial that we have over here. And it's actually not that difficult for this psi function that we have over here to estimate this polynomial that we have over here, or at least the a terms, the a coefficients that we have over here. And the reason behind that is because of the fact that for this polynomial, what we can simply do is run an ordinary squares regression of y on, well, a constant, on psi x squared, on psi x to the power 3, etc. And then we get all these a terms that we have over here, these a j coefficients. We can estimate them by simply using ordinary squares. Of course, that doesn't give us yet our estimator for g hat, but then what we can do is that we can just add them up in this way that we have over here in order to get our estimator. So series estimation is as simple as that. It's extremely simple in that sense. It only, say, trying to, with ordinary squares, trying to estimate these coefficients that we have over here and calculate our function by this function that we have over here. Even though series estimation by itself, doing it is very simple, the econometrics behind series estimation is actually quite hard, but they were already described quite a long time ago, more than 20 years ago, by Don Andrews in an Econometrica article in 1997. not going to say too much about this, but in practical situations, what a main question now arises is, what kind of psi-x should we use? Well, there's nothing said in the Weierstrass approximation theorem what to do in this case, but therefore we can make it ourselves as simple as possible. What we could do is that we could simply use psi-x equal to x, which means that the only thing that we need to do is that we have to run a regression of y on a constant, on x squared, etc. And then we simply are going to calculate our function by this, say, formula that we have over here. It's as simple as that. That brings me to the benefits and also to the drawbacks with respect to series estimation. A benefit of the use of series estimation is that it's, of course, extremely easy. Even though kernel regression these days is also not that difficult anymore, there are many statistical packages that can do kernel regression estimation for you. You should realize that kernel regression estimation is still, well, it is actually somewhat hard. That is not for series estimation. The only thing that you need to do for series estimation is simply run a regression. That is very simple to do, and there, in a sense, any kind of statistical package would be able to do series estimation for you, because the only thing that you need is simple ordinary squares. So that's a good thing to say about series estimation. However, you should also realize that there are also drawbacks with respect to series estimation. And that has all to do with the fact that you should realize that there is a difference between kernel regression and series estimation. What you could say is that kernel regression is a local method, whereas series estimation is a so-called global method. What is this difference? Well, with respect to kernel regression estimation, what you're going to do is that you're only going to use those observations that are very close to the point in which you would like to estimate your function gx. So to come back to this model that is over here, suppose that you would like to estimate this function g in a particular value of x, say 0, 1, or 2, then at that moment in time, at the moment that you're going to use kernel regression estimation, then you're only going to consider those observations that are very close to that particular value x in which you're going to estimate your function g. That is very good. It's, first of all, it makes you very flexible because of the fact that you don't have to take into account the shape further into the, say, data that you have. So at the moment you would like to calculate g in 0 or 1, then you don't have to take into account how that function might look like at the moment that x is not equal to 0 or 1, but for example, at the moment that x is going to be equal to 10. So that makes it actually quite flexible, a kernel regression estimation. It's also very good because of the fact that that implies that at the moment that you're going to have, say, outliers, then these outliers are only going to have an impact for those, say, observations that are going to be very close. So those x's that are going to be very close to that particular outlier, they're not going to have any impact further away. Well, that's not true at the moment that we're going to look at series estimation. The moment that we're going to look at series estimation, all the outliers have a so-called global impact. In series estimation, what you're going to do is that you're going to use all the information, all the observations in your data set in order to estimate your polynomial. And that implies that an outlier, say, very far away, could still have a very big impact. And that is actually one of the drawbacks with respect to series estimation. That brings me to the next non-parametric regression estimator, and that is local linear regression. What local linear regression tries to do is, well, to bring together all the, say, good things with respect to both series estimation as well as with respect to kernel regression estimation. What you should realize is that I just said that kernel regression estimation is a local estimation method, and that makes this estimation method very flexible. That is to say that at the moment that you would like to estimate your, say, function gx somewhere in a particular point, say 0, 1, or 2, then you don't have to take into account the shape at, say, other points. That is actually quite a nice thing with respect to kernel regression estimation. However, it also has one drawback, and that is that kernel regression estimation actually assumes that in an area locally around this x that we have over here, the regression function, this gx that we have over here, is going to be constant. So it's completely constant in an area around this x that we have over here. Of course, it's going to be a small area, but you should realize that that's what kernel regression assumes. That is quite different from series estimation because of the fact that series estimation assumes a particular kind of polynomial for this gx that we have over there. And that means, of course, that for any different x that we are going to look at, even at the moment that we're going to look at two x's that are very close to each other, they will have different values because of the fact that that's what the polynomial says. So therefore, you should realize that even though maybe, well, this global series estimation is less flexible because of the fact that you're going to estimate this, say, polynomial for all the data, and therefore you have to take into account how the shape is at, for example, x is equal to 20. At the moment that you're going to calculate gx in x is 0, you should realize that it also has one very nice thing, and that is that it doesn't assume any, say, constant relationship with respect to this gx, even not locally. In that sense, what we could do is that we could, well, try to use a local method where we're not going to assume that gx is going to be constant. We could extend this a little bit by simply assuming that gx is going to be a linear function, even at the moment that we're going to consider it very locally. So instead of assuming it to be constant, we could assume that gx is going to be equal to a0 plus b0, z minus x, in this area z, where z goes from x minus epsilon to x plus epsilon. Where epsilon, of course, is going to be a really small interval, say the bandwidth as we have introduced it before. Well, now you might, of course, say like, well, but this is still very restrictive because of the fact that now what we're going to do is that we're simply going to assume that there is a linear relationship with respect to g. Well, that's not completely true because of the fact that we're only going to assume this to be locally the case. It's only in a very short interval, this interval that we've over here, that we have this local relationship. As soon as we are outside of that interval, we're going to, of course, have another linear relationship with another a0 and a b0. Well, this is the whole idea behind local linear regression. The question then, of course, arises, how are we going to estimate this a0 and b0 for any x that we have over there? Well, that we can do by minimizing this criterion function that we have over here. It's a sum over, first of all, this difference that we have over here, but squared. We are going to multiply that by this kernel function that we have over here, the kernel weights that we have over here. Well, let's first of all, well, ignore this, say, kernel function that we have over here, and just look at this part that we have over here. This is actually nothing else as the residuals. These are the residuals of this regression function that we have over here for a regression of a constant, and on this xi minus x that we have over there. These are the residuals but squared, so that means that if we ignore this kernel function that we have over here, then this is actually nothing else than a sum of squared residuals. So at the moment that we're going to minimize this, we simply get the results with respect to ordinary squares. But take into account that what we in fact do is that we're going to multiply this by this kernel function that we have over here, which means that actually local linear regression, well, in that sense, can be simply seen as some form of weighted least squares. We're going to weight the observations that we have over here. Well, and we're going to weight it according to the distance between xi and x. That means that those observations that are very close to this x, in which we would like to calculate or estimate our function gx, they're going to have a lot of weight. Those observations that are too far away, they're going to have, well, very few weight or even no weight at all. So that's the whole idea behind local linear regression. To give you a little bit more of an idea what local linear regression does, what we can do is that for the moment we can assume that b0 is equal to 0. Of course, that's not what we do in local linear regression in general. We are going to both estimate A0 and B0 in order to get this gx that we've over there. But what we could do is, for the moment, assume that B0 is going to be equal to 0. Then the only thing that we need to do is to minimize this function that we have over here. Well, that's not that difficult because of the fact that it is immediately seen that this is going to be our first order condition in that particular case. What we need to do is that we have to take the first order derivative with respect to A0 as we have it over here. Well, that is this thing here at the left-hand side. And of course, we have to set that equal to 0. Well, then the first thing we can do is that we can divide the left and the right-hand side by -2 in order to get this thing that we have now over here. And then the next thing we can do is that we can get rid of the parentheses that we have over here. Then we get k, our kernel function, multiplied by y, and then another time our kernel function multiplied by -a0. So therefore we get then this relationship that we have over here. Well, then the next thing that we can do is that we can, well, realize that a sum of a difference is a difference in sum. So therefore we get this relationship that we have over here, and then we can bring this to the other side in order to get this relationship that we have over here. And then we finally are going to divide the left and the right hand side by this sum that we have over here, then we get exactly the thing that we have here at the end. So the estimator for A0 is going to be this thing we have here right hand side. Well, this should be looking very familiar to you because of the fact that that is exactly the kernel regression estimator. So that means nothing else as that you could say that local linear regression is more general than kernel regression estimation. Or the other way around, you could say that kernel regression estimation is a special case of local linear regression in the sense that we are going to set the B0 that we had the previous slide, this B0 that we have over here, we set that equal to 0. That means, as I already said, that you could actually say that what kernel regression does is that it's going to assume that locally our gx function can be represented by a constant A0 that we have over here. So in that sense, you could also call kernel regression estimation local constant regression estimation. And that brings me to the next topic, and that's the topic of local polynomial regression. The question that arises, of course, we now have been looking at a situation in which we're going to assume the function g to be either constant or linear, but the question that arises is why should we actually stop with a linear function? Why can't we also look at higher order terms? For example, quadratic term, a quartic term, or even a cubic term. Well, that we could do, of course. We could here, instead of looking at a linear function, we could look at the polynomial function. Then what we're going to do is that we're going to minimize this criterion function that we have over here, where we again have A0 and B0. But in addition to that, we are going to have here C0 for the quadratic term. But of course, we can additionally add a quartic or a cubic term here in addition as well. That makes, of course, the prediction function much more flexible because of the fact that then we are going to allow for higher order terms that we have over here. Well, in that sense, it's good to remember the things that I said in the previous video. In the previous video, I said that, well, more flexible models are not always going to be better predicted. So now the question, of course, arises, how do we know whether, say, local polynomial regression for a polynomial of a particular size is going to be a better predictor in terms of machine learning? Well, for that, we can do, of course, cross-validation. That means in this case that we can, in terms of local polynomial regression, look at cross-validation for two things. First of all, we can look at h, the bandwidth that we have over here. But in addition to that, we can also look at the number of terms that we're going to include in our local polynomial regression. Okay, that brings me back to the example that we have looked at before. Well, actually, I have extended the example a little bit. Remember that we had at the left-hand side yi, and at the right-hand side we had 2 minus half xi squared. plus cxi plus the sinus of 4x plus ui. Now I'm going to assume that this is only going to be the case at the moment that xi is going to be positive. At the moment that xi is going to be negative, then at that moment in time, we're going to have the sinus of 16xi plus ui. Still, I'm going to make the assumptions as what we had before. Xi is going to be uniformly distributed between -1 and 2. And ui is going to be normally distributed with a mean equal to 0. And 0.25 is going to be the variance. And now what we would like to do is that we would like to do cross-validation for series estimation, kernel regression, and polynomial regression. And it would now be so nice to see which method is going to perform best. And what I'm going to do is that I'm going to use a test sample for this. So again, we are going to have a test sample of the size of 10,000 observations. And based on this test sample, we can compare the different estimation methods with each other. And the results, they are at the next slide. What we are going to do is that we're going to look at linear regression, series estimation, nearest neighbor estimation, kernel regression, and local linear regression. And then based on that, we have here, first of all, the optimal values. I'm going to explain that in a minute because of the fact that, well, these things are, of course, different for the different estimation methods. And we're going to look at the test risk. The first estimation method I'm going to look at here is linear regression. With respect to linear regression, there is nothing to choose because of the fact that then what we're going to simply do is that we're going to run the yi's on a regression with just a constant and a linear term xi. So then what we're going to get in that particular case? Well, then we're going to get this picture that we have over here. Remember that we have, of course, on the x-axis, we have the different values of x that run from -1 till 2. And on the y-axis, we have either the outcomes or we have, say, our prediction function. And in addition to that, we have our best predictor that now looks like this orange curve that we have over here. And you realize that especially this part over here for negative values, that one is difficult to predict because of this high frequency sinus that we have over here. And the first thing that we're going to do is that we're going to try to fit this model with respect to linear regression. Well, we immediately see that that's not that great. Again, comparing with the best predictor, we do see that actually linear regression doesn't do well almost anywhere. It doesn't do so well over here, but even over here, it, well, is not doing so well. And that is also the reason that at the moment that we're going to look at the test risk, that the test risk is by far the highest at the moment that we are going to look at linear regression. Apart from linear regression, we can also look at series estimation. There we do have to choose an optimal value because in series estimation, what we're going to do is that we're going to run a regression of y on a constant, on xi and xi squared, etc. And then, of course, what we do need to make a decision about is what is going to be our best performing model in terms of the number of terms that we're going to include. Well, for that, we are going to use cross-validation. And after I've done that, I found out that the optimal value was as high as 12. So that means that we're going to, well, include 12 terms in our polynomial, starting, of course, with the constant, then xi squared, etc. Up till, of course, xi to the power 12. Well, then at that moment in time, you're going to see that the test risk is going to be reduced by quite a lot. It's about half the size of what we had with respect to linear regression. And also here we can look at our picture and we immediately see that, of course, this model is going to, well, predict our regression, or in fact, our best predictor much better than what we had before. You now see that the difference between our best predictor and this predictor that we have over here, that we have been estimating, based, of course, on series estimation, is much better than what we had before with respect to linear regression. Still, this part, of course, over here is relatively not that well predicted. Now let's go on with another method, and that is nearest neighbor. We already know that nearest neighbor is actually also a kernel regression estimator. And in this case, we are not going to choose the bandwidth, but instead as usual we do with nearest neighbors, we are just going to, well, calculate the K. And in this case, after doing cross-validation, we find an optimal value equal to 6. And we are going to see that the test risk is further reduced from roughly 0.60 to 0.49. And also here we can again look at our picture, and we do see that we essentially perform somewhat better than what we were before. And we also see here that especially here at the bottom of this, of the axis, we do perform somewhat better than what we had with respect to series regression. Well, let's go on with the next method, and that's the method of kernel regression. Now you might immediately say like, well, hey, but nearest neighbor is also a kernel regression method. That's true. But now what we're going to do is that we're going to look at another kernel. The kernel that we are going to use over here is going to be the Epanechnikov kernel. And then what we can do is that we can choose the bandwidth. So cross-validation is now in this case based on the bandwidth. And we do actually find that at the moment that we do cross-validation, and we're going to look at the test risk, that the test risk is even further reduced. So now at the moment that we're going to look at the results with respect to kernel regression, we do see that, again, kernel regression seems to do a little bit better than nearest neighbors, the previous method that we have been looking at. And then finally, we can look at the final one that we have over here, local linear regression. I have not been looking at local polynomial regression. That is something that I could have done, and look at higher order terms and look at how well they actually do. But I haven't done that. But if we're going to simply look at local linear regression, well, the bandwidth is then going to change a little bit, but the test risk is even further reduced. So therefore, now we see that local linear regression is going to be our best performing model. And that's also what we see in this picture, especially here at bottom, even though I did say that the bottom is, of course, very difficult to estimate, but we do see with this relatively small sample size that we can do actually pretty well with respect to our prediction function. I would like to go on with the final topic, and that is the curse of dimensionality. In order to introduce this topic, maybe the best thing to do is actually to scroll back a little bit and to look at this slide that we have over here. This is just a slide that we have seen before. And what you should realize is that what I have done is that I have sorted here the methods a little bit. What I have done, I didn't really say that, but what I've done is that I actually placed the worst performing methods first and the best performing methods at the end. But we should realize that at the moment that we're going to look at these methods that we have over here, then the first two methods that we have over here are so-called global methods, both linear regression as well as series estimation. They're global methods, whereas the last three methods that we have over here, nearest neighbor, kernel regression, and local linear regression, they can be all described as local methods. And that gives us the idea that generally at the moment that we would like to make predictions, that local methods are going to be making much better predictions than global methods. But that is not generally true. And the reason behind that is related to the topic that we are going to look at right now, and that is the curse of dimensionality. What you might say is that probably really local methods will always do better than global methods at the moment that we're going to look at one-dimensional problems. However, at the moment that we're going to look at higher dimensional problems, and especially at very high dimensional problems, then in that particular case, it may be possible that these local methods, they have one particular problem, and that's the curse of dimensionality, and that might make them not that good predictors. In order to understand that, maybe the best thing to do is to start with a case in which we're going to assume that our features, that they're going to be discrete. And we even are going to assume here that they are going to be dummy variables. And let's first of all start with a very simple case in which P is simply equal to 1. Of course, later on we're going to look at higher dimensions, but at this moment in time we're going to assume that P simply is equal to 1, so we are in the one-dimensional case. Then we actually already know how to predict in the discrete case. We know already how to make the best predictor because of the fact that we do already know from the example that we had before with one-bedroom flats, that then what we should do is that we should take the sample average over, say, the xi's that are equal to the thing that we would like to predict, this x that we have over here. And we should realize that x in this case, because of the fact that we have dummy variables, can only be equal to 0 and 1. So that means essentially that at the moment that we would like to predict for x equal to 0, then we simply take the sample average among those observations that are equal to 0, for which xi is equal to 0. And at the moment that we would like to predict for x is equal to 1, then we are going to take the sample average for those observations for which xi is going to be equal to 1. It's as simple as that. Now, the main question that arises is how many observations are we going to use here with respect to our estimator? Well, that depends a bit on how this x is distributed, but let's look at a situation in which x is completely well distributed, so it's 50-50% distributed. That would mean that we are going to use here for our predictions, we're going to use 50% of the observation. So that means that if we would have 1,000 observations, then in that particular situation, we're going to use 500 observations for a prediction for xi equal to 0. And we use 500 observations for the case that xi is equal to 1. Well, that will work all fine. But what is going to happen at the moment that we're going to increase the dimensionality, for example, to p is equal to 2? Well, then still things are going to be relatively simple, because now at the moment that we still have dummy variables, that means, of course, that we have 4 different outcomes. Either both x's could be equal to 0. It could be the case that both x's are equal to 1. And it could be the case, and these are 2 additional cases, that one of the x's is equal to 1 and the other one is equal to 0. Well, that means that, of course, that we're going to have 4 potential outcomes, but that the idea is exactly the same. What we're going to do is that we're going to make our prediction for these 4 outcomes based on this estimator that we have over here. So if we would like to predict that, say, for a situation in which both x's are equal to 0, well, then we simply are going to take the sample averages among those observations for which both x's were equal to 0. Again, the question arises, how many observations are we going to use with respect to the different predictions that we're going to make? Well, again, that depends on the x, how the x is distributed, but actually it also depends on how the x's are distributed with each other. If we're going to look at the, I would say, best case scenario, if we're going to assume that the x's are both 50-50 distributed and they're independent from each other, well, then in that particular situation, we are going to use 25% of the data for any kind of, say, prediction that we're going to make. So that would imply that if we would have 1,000 observations, then 250 observations are going to be used for any kind of prediction that we have. Also, this still sounds pretty good. However, what is going to happen at the moment that we do not have p is equal to 2, but suppose, for example, that p is equal to 10. Well, then at that particular moment in time, you should realize that the number of combinations that we're going to have is then going to be equal to t to the power p. And if p is equal to 10, that means, of course, that we are going to have roughly 1,000 different combinations that we could actually have with respect to different x's. And that means, again, that at the moment that we're going to assume that we're in the best case scenario, that the x's are going to be all 50-50% distributed, and they're even going to be independent from each other. Well, that would mean, of course, that the percentage that we're going to use is simply going to be equal to half to the power p. Well, that, for example, would imply that at the moment that we have 1,000 observations, well, that would mean that if p is equal to 10, then every combination, every prediction that we're going to make is then only be based on a maximum of one observation. That is, of course, not that much. If we're going to make our prediction just on one particular observation, then the variance is going to be high because of the fact that at the moment that particular observation is going to be an outlier. Well, then, actually our prediction is going to be an outlier as well. So you should realize that this is not that great anymore, and take into account that things become even worse at the moment that we are not in the best case scenario. In the case that the x's are not 50-50 distributed, or they're going to be dependent upon each other, well, then things may actually be even worse. Well, now you might, of course, say like, well, this is only a problem in the discrete case. Well, that's actually not true. The same problems are going to arise at the moment that we're going to look at the continuous case. However, in the continuous case, as we already know, we cannot use this estimator that we have over here. But then in that particular moment in time, we should use another kind of estimator, such as, for example, the k-nearest neighbor estimator that we have already seen before. Let's now look again at a situation, first of all, in which p is going to be equal to 1. And suppose that what we would like to do is that we would like to cover 10% of the data with respect to our nearest neighbor estimator. So we would like to, any prediction that we're going to make, we would like to cover at least 10% of the data in order to have not that high variance, of course. That means, for example, that at the moment that we're going to have 1,000 observations, that would mean, of course, in terms of the k-nearest neighbor estimator, that k is going to be equal to 100. Well, what does that mean? Well, that means, for example, at the moment that x is going to be uniformly distributed between 0 and 1, but then at the moment that we would like to predict x equal to half, that roughly means that we are going to use observations between 0.45 and 0.55 with respect to this x. So all those observations which have a value between 0.45 and 0.55 will then be used in order to make our prediction. What can we say about that? Well, not that much, of course, but generally we might expect that the bias is not going to be that large, neither the variance, because we use 100 observations, which is quite a lot, of course. And we should realize that even the bias is not expected to be very large because of the fact that we're going to use a relatively small interval to make our predictions. We could say that the observations that we're going to use are still quite close to the, say, thing that we would like to predict, x equal to half. But now suppose that things become more difficult, and we're going to assume now that p is not equal to 1, but p becomes equal to 2. And in addition to that, I'm going to assume again that x1 and x2, they are going to be uniformly distributed, and they're even going to be independent from each other. That again is going to be what you could say a best case scenario. Now, of course, the question arises, at the moment that we would like to, for example, make a prediction equal to x1 and x2 equal to half. So what we would like to do is suppose that we would like to make a prediction for the case that both these x1 and x2 are going to be exactly equal to half. Well, then the question arises, what should we do in terms of this interval that we have over here? What interval do we, in a sense, obtain at the moment that, again, we would like to cover 10% of our data? So again, at the moment that, in the case that we have 1,000 observations, we would like to use k equal to 100. Well, in the case that we're going to look at the two-dimensional case, we're not going to get an interval, of course. We're going to get a circle. And the question now arises, of course, is what is going to be the radius of that particular circle? What radius are we going to have around 0.5, 0.5 of values of x1 and x2 that are going to be used for our estimation? Well, since we see here that at the moment that we are going to look at this interval, that interval is, of course, of a length of 0.1, but half of that is going to be equal to 0.05. So that might suggest that the radius that we could use in this particular case should also be equal to 0.05. But that's actually not true. And the reason behind that is because of the fact that if we are going to then look at what is the probability then that a particular, say, observation is in that particular circle around 0.5 and 0.5 with this radius that we have over here, well, that's only equal to 0.05 squared times pi, and that's only 3.1%. So in that particular case, we're not going to get, say, 100 observations out of 1,000, but we're only going to get around 30. So that's not too much. So therefore, what we need to do is that we have to increase the radius. Question, of course, arises, how large should that radius be? Well, that's going to be equal to, in this case, the square root of 0.1 divided by pi. That's roughly equal to 0.18. So the radius should not be equal to 0.05, but it should be equal to 0.18. What does that mean? Well, that means, among other things, that if we're going to predict this x1, x2 equal to half a half, and we have an observation that for which x1 is exactly equal to a half, then, well, the observation for x2 could be roughly in between 0.3 and 0.7. So that is already quite a big difference, of course. But what is going to happen at the moment that we make p, our number of regions, even larger? In general, what we can say is that the sphere, so that's the higher dimensional circle, the sphere should have a radius equal to this thing that we have over here, where the 0.1 over here comes, of course, from the 10% that we would like to cover. Then you should realize that at the moment that p becomes equal to 10, then this radius that we have over here becomes equal to 0.723. To give you an idea of how large this actually is, take into account that the axes that we had so far were assumed to be uniformly distributed, so they can only take values in between 0 and 1. So at the moment that we would, for example, like to make a prediction where all the x's, x1 till x10, are going to be equal to a half, well, then you should realize that if we have an observation for which x1 till x9 is roughly equal to a half, the next could be anything, because of the fact that you should realize that you cannot be more than a half from a half. And therefore, well, if you're allowed to be even as far as 0.7 from a half, then of course x10 could be anything, even in the case that the x's are not exactly equal to each other, or equal to a half over here. We should realize that then still x10 is allowed to be actually anything. And that means, of course, that what we're going to get in this case is that we most likely are going to have a very high bias. And the reason behind that is because of the fact that now we are going to allow observations that are, at least with respect to one particular characteristic, completely different. They're still going to be allowed to be in our estimation method. So this is going to give us a very high bias. Now you might, of course, say like, well, but that we can do something about that, because of the fact that we have chosen k to be quite large, equal to 100, or at least we try to cover 10%. Maybe we can reduce that. But that will definitely reduce the bias. It will generally reduce this radius that we have over here. But you should take into account that even in the case that we're going to say that we're only going to have to cover 0.1% of data, well, then at that moment in time, I'm not going to get here 0.1, but I'm going to get a 0.001 over there. And then even in that case, you should realize that the radius that you have to have is as large as this one that we have over here. And you should therefore realize that even in the case that you're going to have this, say, relatively small value that we have over here, you're still going to have some bias over here. In addition to that, you should also realize that if you're only going to cover 0.1% of the data, that means, of course, that if you would have had only 1,000 observations, that would, of course, imply that you're only going to have a nearest neighbor estimate of k equal to 1. Well, that generally has a very high variance. So therefore, we're going to see that because of this cursor dimensionality that we have over here, that, well, local methods, all local methods, not just the k-nearest neighbor estimator, but actually every local method has this problem with the cursor dimensionality. Therefore, these local methods can actually have very high variances, and therefore, actually, they may not be always good predictors in the cases that this p that we have over here is going to be very high. And you should realize that global methods do not have this problem. And the reason behind that can be best explained at the moment that we're going to look at linear regression. At the moment that we have the linear regression model, then you should realize that the prediction that we're going to be making is always based on x multiplied by beta. And even though x could be highly dimensional, x multiplied by beta is always going to be one-dimensional. And that means that the linear regression model makes a very restrictive assumption. And that is to say that what it does, it brings back in one time the dimensionality from, say, any kind of p that we can have over here to a one-dimensional index, this x multiplied by beta. That's what linear regression does, and that's actually also what, in fact, any kind of global method does. But you should realize that even though that's very restrictive, that also completely solves the cursor dimensionality, because of the fact that we now see that actually everything is only based on a one-dimensional index, x multiplied by beta, and it really doesn't matter how high the, say, dimension of that x is going to be. At the end of this video, I would like to look at a particular empirical example. This is based on house prices in Gothenburg, and I will be coming back a couple of times during this lecture series with respect to this example. What I have done is that I have downloaded around 11,000 apartments from a website which is called bully.se. These apartments were sold in a period from 2012 to 2021, and what I would like to do is that I would like to predict the sales prices with respect to the number of squared meters that we have over here. So I do have the house prices, I have the final selling prices, and then what I would like to do is that I would like to predict them based on a particular number of variables or features. What I'm going to do is that I'm going to use the area in square meters up to a quartic, year, area interacted with year. We are going to have a month, zip code, floors, years of construction, the rooms, and distance to sea, as well as the rent that you have to pay. A little bit strange in Sweden at the moment that you have your apartment. So if you own it, you still have to pay rent. Well, what we are going to see is that we're going to use here one half of the data as a training data set, and the rest we are going to use for test. And now we're going to see that the test risk is going to be equal to 0.0287. We're going to compare that later on with other methods. And we are going to, in addition to that, see that the R squared based on the test data is going to be equal to 0.796.